Today we're deriving Schrödinger's time-dependent wave equation, which is like the F equals ma of quantum mechanics. First, we're going to start with the idea that total energy is equal to kinetic energy plus potential energy. Then I'm going to replace kinetic energy with 1/2 mv squared, which you're probably familiar with if you've taken any physics classes. And I'm going to replace potential energy with the variable u. Now, 1/2 mv squared can be rewritten as mv squared over 2. Now we know that momentum is equal to mv. So what we can do is we can say mv quantity squared over 2m is equal to momentum over 2m, momentum squared over 2m. Okay, so now I'm going to plug this in to our kinetic energy. Or I guess it's just rewriting the kinetic energy formula that we already have. Okay, and now I'm going to multiply everything in this equation by the wave function psi. So I'll have E psi is equal to, I'm going to write this as 1 over 2m times p squared and then psi plus u psi. Okay, now psi is equal to, psi is the wave function with inputs x and t, and it's equal to e to the I kx minus omega t. So now we're going to do some partial derivatives here with respect to x and t. I will start with x, first partial derivative of psi with respect to x. And that's going to be, we're ignoring the t because we're just taking the derivative with respect to x. So we're just going to have ik times this whole thing, and since this whole thing is just psi, I'm just going to write psi. I'm not going to write the x and t every single time because it takes a while. And now the second derivative of psi d squared with respect to x is just going to be the same thing except squared. So we have ik squared times psi. Now the derivative with respect to t, I'll write it here, is, now we're dealing with the t part and ignoring the x part, but the I is still part of the t, so we have negative I omega times the whole thing, which is just psi, times this whole thing. Now I want to figure out, first of all, how to rewrite this, because I is the imaginary number square root of -1. So if we square the square root of -1, we just get -1. So this can be rewritten as negative k squared times psi. Now I want to be able to plug this in up here for p squared psi, and so I need to turn this k squared into a p squared somehow. And I'm going to use the momentum of a particle to do that. So momentum of a particle is Planck's constant divided by the wavelength. And the wavelength is 2 pi divided by k. So if we plug this wavelength formula in here, we will get p equals h divided by 2 pi, Planck's constant divided by 2 pi, times k. And h over 2 pi is the reduced Planck's constant h bar. So if we solve for k in this expression, we get k is equal to p over h bar. And now we can plug that in over here. And we will get negative p squared over h bar squared times the wave function. And now you can see we have a p squared psi, which we can plug in up here, but I want to move the h bar and the negative sign over to the other side of the expression. So that's what I'm going to do. I'm going to multiply both sides by negative h bar squared. So I'll have negative h bar squared times the second derivative of psi with respect to x is equal to p squared psi. Now I'm going to plug this in for this in the original energy equation. So I have E psi is equal to 1 over 2m times, actually I'm going to write the negative h bar squared up here, and then I'll put the second derivative here, and then plus u psi. And this is the time-independent wave equation, so we only have a few more steps to go to get to the time-dependent, and we're going to be dealing with this derivative now. So what we have is, I want to replace E psi here, so I need to get an E psi on this side. So E, the energy of a particle, is Planck's constant times frequency. Now if I multiply this by 2 pi divided by 2 pi, which is just equal to 1, so it doesn't change the expression, I could separate this into h over 2 pi times 2 pi k, or sorry, 2 pi f. And now, we already saw that this is the reduced Planck's constant h bar, and 2 pi f is equal to omega, the angular frequency of the wave. So we get energy is equal to h bar omega. So now we have an omega up here, but how do we get the h bar there? We can multiply both sides of this equation by h bar, and then since I don't want the negative I there, I'm going to also divide both sides by negative I. So we can rewrite this. I'm multiplying both sides by h bar first. I'm also dividing both sides by negative I. So we'll have this on the left side, and that's equal to, I divided out the negative I, and I'm multiplying in the h bar, and then we have omega psi. So this is just E, remember. So this whole side is the same as E psi, which is what we were looking for up here. So I'm just going to plug this in for E psi, and then that'll be it. But first I want to rewrite this because it looks kind of ugly. So I know that 1 over negative I, if we multiply that by I over I, we can get I divided by negative I squared. And we said before that I squared is negative 1, so we'll have I over negative 1, which is the same thing as I over 1, which is just I. So we can rewrite this side as I h bar d psi dt. So I'm just going to plug that in up here, and we'll have that is equal to negative h bar squared over 2m d squared psi dx squared plus u psi. And remember, psi is the wave function, so all of these technically have the inputs x and t, but I just abbreviated everything to psi. And also the u is a potential energy function, so it will also have inputs x and t. And that is the time-dependent wave equation.